I'd like to talk about EOS, the architecture of Arista's operating system. You know, you just don't get that many chances in your life to create a new commercially viable switch operating system from scratch. I've had exactly one chance to do that, and we at Arista were determined to make the most of that chance, to do something fundamentally better, to push the state of the art in how switch operating systems work. Of course, the most important attribute of a switch software stack is stability. Does it stay up? Does your network keep running? Downtime in the network is a disaster. So how do you make a switch operating system as stable as possible? And thinking along those lines was what led us to the switch operating system architecture we call the state sharing architecture. We were well aware of the legacy approaches and the problems that they give rise to. And what I'd like to do in this talk is explain the state sharing architecture, how it leads to a more stable and more resilient operating system, and specifically, at a level of fine technical detail, where do the conventional architectures fall apart, and how does the state-sharing architecture maintain stability in those cases? In this talk, I'll get a little more technical than I usually do, because I think it's important to understand the details of the competing architectures to understand how the right architecture leads to a more stable network, a more stable switch. So first, I will go into detail about how the EOS architecture works, the state-sharing architecture. And then I'll contrast that to the more traditional message passing architecture and show how the state sharing architecture solves some key stability problems you encounter with message passing. EOS is built on an architectural component called NetDB. This is a network-wide database that retains all of the state associated with the network and the networking devices. At the core of NetDB is SysDB, a system database on a single switch. Within SysDB, we store all of the state of switching. Which links are up and which links are down? What routes have we learned from which neighbors? Which VLANs are assigned to which ports? What are the temperatures and the power supply voltages and all the counters? All of this state is stored in SysDB. SysDB is a true database in the sense that its only job is to hold state, validate updates to that state, and make those updates visible to other processes. In particular, SysDB does not care what the state means. There is no spanning tree specific code in SysDB, no routing specific code. All of the different aspects of state are just different tables of data as far as SysDB is concerned. Now, beyond that, we're about as far from a commercial database as you can get and still call yourself a database, because SysDB is not persistent, it's not transactional, it's not relational, it's not SQL-based, it's not even query-based. SysDB is in-memory, object-oriented, hierarchical, publish-subscribe-based, atomic update-based. But still, it's this true database in that key sense that it's all about holding and managing the state. So within that context, we can add some other processes that exist in the EOS system. For example, we have our ASIC driver process. We call it the forwarding agent. And this is a process whose only job is to take care of the ASIC that forwards packets. It needs to load control plane information, like routes and topology information, into the ASIC, and also respond to ASIC events, things like counters changing, interrupts, or things like link down events. Then we have some other processes in the system. There's actually quite a few. I believe we have about 100 in the current version of EOS, but I'll stick with just 2 for simplicity. We'll have our LACP agent that's responsible for running the link aggregation control protocol, and we'll have our humble LED agent, a process whose only job is to keep all of those little link LEDs on the front panel the right color. So think about what happens in the system when a link goes down. There's an interrupt. The forwarding agent receives the interrupt, checks the interrupt cause, and realizes, oh shoot, the link went down. And it then updates an object in its address space, changing one attribute, a link status attribute, from link up to link down. Then our middleware kicks in and propagates that update to the system database. The system database validates the update, makes sure that the ASIC driver process is allowed to write that portion of the database, makes sure that the update is legal within the schema of the database. That is, you can write a link to link up, you can write a link to link down, but you can't set it to 17. That would be invalid. We'd reject the update and disconnect the process. Once the update passes those checks, we then propagate the update to all of the processes on the box that care about link down, which on a switch is pretty much all of them. But taking just our examples, the LACP agent needs to know that the link went down to withdraw the link from the aggregate, and our humble LED agent responds to the link down event by turning off the link LED. So that's how things work when everything's going well, but what about when the box encounters a problem? Suppose Dr. Evil logs into our box and sends the LED agent a SIG-stop signal. This is a Unix signal that prevents the process from executing any more instructions at user level, effectively introducing a hang into the system. What's going to happen? Well, the administrator can go to the box and pull a link, and what you'll see is that the link LED stays green. And this looks pretty bad, right? If you've got a NetOps background, when you pull a link and the link LED stays green, oh boy, time for a therapeutic reboot. But with our box, if you look carefully what actually happens, you'll see that all of the link down processing has actually taken place. SNMP sent its trap, OSPF withdrew its routes, LACP pulled the port out of the aggregate, the CLI shows the link is down, because the only thing that didn't happen is that the LED agent, because it had been SIG-stopped, didn't process the update from sysdb. Now, suppose that you then take your cable and go in and out and in and out and in and out of the switch, links going up and down and up and down and up and down. Updates are getting queued up between the system database and the suspended LED agent. That queue gets bigger and bigger. And at some point, our process manager becomes impatient with the LED agent because it's not making any forward progress. So the process manager kills the LED agent and starts a new instance. And the question is, what do we do with all of those queued update messages? You'd think they're pretty important, right? How do you get the system into the right state if you don't save all those messages? Well, with a state sharing architecture, it's easy. I can throw all those messages out. I don't need them. They're not precious, because when the LED agent starts, it does the exact same thing it did when it booted the first time. It mounts the state it needs from sysdb, which is the interface status, walks across those interfaces, changes all the link LEDs to be the right color, and then goes back to waiting for updates, which is all it was doing in the first place. The key thing to observe here is that we don't need to save those update messages, and we don't need any special restart logic, because the agent's ordinary initialization logic also handles the restart case. So elegance of restartability is one of the key advantages of the state sharing architecture. The second advantage is a little harder to see, but it's actually the more important advantage, and that's what happens in the system when the rate of updates of some piece of underlying state fundamentally exceeds the rate at which the receiver of those updates can process them. So for example, suppose you're pulling links in and out of the switch like crazy, so ports are bouncing up and down like there's no tomorrow, and so updates are flying to the system database, they're getting into the queue for the LED agent, but the LED agent just can't process them quite that fast. It just takes longer to program the LEDs than you might expect. And so the queue of updates gets bigger and bigger as the LED agent falls farther and farther behind. You can't queue updates forever. You can't build this queue out to infinity. So what's going to happen? Well, in a state sharing architecture, you can do a marvelous thing. Here's what we do. When our socket buffer fills up, we simply stop putting updates into it. Instead, the system database remembers, oh, this interface object has some state that's newer, state I have not been able to propagate yet to the LED agent. It's sort of on a dirty list, we call it, a list of dirty objects that have to be cleaned by having their updates propagated out to the LED agent. And as the LED agent falls behind, a list of dirty objects gets built. The size of that list is fundamentally bounded to the number of objects in the system, unlike a queue of updates that can grow without bound forever and ever. So in the worst case, you wind up with every interface on the box on the dirty list. Sooner or later, we hope, if the LED agent's making any progress at all, it dequeues some messages and some space frees up in the socket buffer. At that point, the system database looks at the list of dirty objects, pulls some things off the front, and puts their now current state into the socket buffer. And that's the key, the now current state. The link could have gone up and down and up and down and up and down and up and down, and then when space opens up in the socket buffer, we put exactly one update in it, saying the link is now down. That ability to coalesce updates, take a lot of updates on the input side, and send just one update to the processes falling behind that gets that process into the right state. That's the key to how a state sharing architecture survives under update overload. It automatically coalesces the updates to reduce the amount of work that the processes falling behind need to do in order to keep up with everybody else. That's how state sharing leads to a stable overall system. So what I've done here is I've illustrated the EOS architecture and how it deals with two key problems: process restart and update rate overload. Let's contrast that with what happens in the more traditional legacy message passing architecture. In a message passing architecture, instead of a system database, you have a message passing service. The idea is that processes inform each other of changes by sending messages, and the message passing service guarantees the delivery of those messages to the receiving processes. So for example, in our system with a forwarding agent, the LACP agent, and the LED agent, we have a message passing bus in between them, such that when a link goes down, the forwarding agent sends a link down message using the message service to deliver that message both to LACP and also to the LED agent. Now think about what happens as links are going up and down, maybe fairly rapidly. So there's up, link down, link down messages coming out of the forwarding agent and being forwarded by the message passing service to the respective agents. Now, imagine that while this is happening, Dr. Evil logs into your box and suspends the LED agent. That queue of messages for the LED agent is growing and growing and growing. And then, finally, the process manager puts the hung LED agent out of its misery and starts a new instance. What do we need to do with those messages? We can't just toss them the way we did in the state sharing architecture, because the only way a message passing architecture can get processes into the right state is by starting from some checkpoint and then redelivering all messages that are newer than the checkpoint. So when the LED agent restarts, it loads some checkpoint of its state, and then, as fast as possible, gets through all those backlogged messages that were waiting for it, that arrived while it was suspended, and ideally will get back up into the right state sooner or later. Now, obviously this process is fraught with peril. Can you actually catch up? Do you have the extra performance to do that? How confident are you that restoring from a checkpoint and replaying messages gets you into the same state you would have been had you simply received all the messages from the beginning? And while you're in that catch-up process, what side effects might you be having on the rest of the system? It's very difficult to make these systems work. Now granted, it's not impossible. This is the way transactional recovery works in commercial databases. It's also the way file system metadata recovery works in a journal metadata file system. But usually you try to put these sort of checkpoint roll-forward recovery mechanisms pretty low level in your software so that each application isn't separately dealing with these issues. Whereas in a message passing architecture, it's intrinsic to the architecture that each process has its own checkpoint and recover logic. Testing all of that is a practical impossibility. The other problem with message passing architectures arises when there's a fundamental rate mismatch, when the source of messages is operating faster than one of the receivers can process them. So imagine links are going up and down quite rapidly, such that messages are arriving at the LED agent at a faster rate than it can actually turn LEDs on and off. The queue gets bigger and bigger and bigger, and what can the system do? The message passing service can't coalesce messages the way the state sharing system did, because the message passing service doesn't know what the messages mean. It doesn't know which messages can be safely coalesced. It doesn't know what final state is required. All it can do is queue more and more and more messages until it runs out of memory, at which point things really fall apart. The system effectively reboots at that stage. I think the instability we've seen in many of our customers' networks from their legacy equipment have this instability as the root cause. Because imagine what happens when you take this bug report back to the vendor and you say, my box melted down, what happened? Instantly, there's a fight that breaks out within the vendor's engineering teams. The people responsible for the forwarding agent say, hey, you guys doing the LED agent, that thing needs to run faster. It's got to process those messages faster to keep up. And the team responsible for the LED agent says, we're processing them as fast as we can. You guys need to throttle back the rate at which you send them. They can't even agree whose bug it is. And of course they can't, because it isn't either of their bug. The bug is in the architecture. And the challenge for legacy vendors is that you can't just change the architecture. You've got to rebuild the whole thing from scratch. So they continue to labor under the burden of the wrong architecture, while Arista is able to move faster, producing software with greater stability, thanks to having the right architecture.